Now that we have seen the generic framework of the EM algorithm and how latent variables can be used, we can introduce a generic framework involving latent variables. Assume that we have observed variables which are denoted by x and unobserved latent variables that are denoted by z. It is common to specify a prior on latent variable p of z, which is a distribution over the latent variable. This distribution can be a Bernoulli, as in the Gaussian mixture example, or other types of distribution depending on the type of the latent variable, discrete, continuous. For example, in variational autoencoders, we will use the Gaussian distribution for the latent variables. It is also common to specify the likelihood p of x given z, since it is often easy to compute the likelihood of x if we know the latent variable z. In this framework, we are interested in several quantities. The posterior distribution p of z given x is useful for inference if we want to understand the generation process behind the data. In our example, it corresponds to knowing from which distribution an observation has been generated. The distribution p of x is useful for density estimation to understand the data, detect extreme behaviors, localize part of the input space in which you have strong or weak dependencies, and so on. This estimation can also be useful if you want to sample more data from this distribution. If your aim is to generate new data, you may need the density p of x, but you can also design methods that directly generate data without first estimating the density. You may think that it is easy to reach these goals because we know p of z and the likelihood p of x given z. Thus, one could compute p of z given x by using p of x z, which is given by the integral of p of x given z against p of z. Unfortunately, this last integral is often intractable in practice because the space z can be of high dimension. Therefore, this integral may not have a closed form expression. Consequently, we need to find solutions in order to approximate this integral. The two most common solutions are Monte Carlo Markov chains and variational inference. In MCMC, Markov chains are used to estimate this integral. The most simple instantiation of MCMC would be to generate many latent variables z and to compute the average of p of x given z times p of z. This quantity converges to the integral of interest, and more involved MCMC techniques can dramatically improve the convergence rate. The main benefit of MCMC is that it targets the true quantity. However, MCMC converge really slowly with many iterations in practice. They are not suited for high-dimensional problems. At the other end of the spectrum, variational inference computes an approximation of p of z given x. Variational inference aims at maximizing a lower bound on the log likelihood. The procedure does not target the true quantity, but an approximation of it instead. However, variational inference is really fast in practice, which is, as you can imagine, computationally appealing. To summarize, MCMC can be really slow to converge but targets the true quantity, whereas variational inference is computationally appealing but may not target the true quantity.